Welcome to the content material for Class 11 of Engineering Statics. You should be watching this video before your 11th class. In this lesson, we will learn how to draw a free body diagram for rigid bodies, and we'll look at the types of reactions that can occur at each possible connection to those rigid bodies. We've already learned how to draw free body diagrams for particles. In today's class, we will learn how to draw free body diagrams for rigid bodies. For example, this beam has 3 joists on it. 1, 2, 3. And each joist exerts a force on this beam. But there must also be some force pushing up on the beam at its connections A and B. But what kind of forces and moments can those connections provide? Today, we will learn what kinds of connections are possible when drawing free body diagrams for rigid bodies. First, we'll start in 2 dimensions. In 2 dimensions, we will consider 5 types of connections. First is a cable. We have already used cables so far in this course. A cable can only exert a force in the direction of the cable. So there is one unknown, the magnitude of the force, because we already know the direction. Second is a roller. In a 2D diagram, we usually use this type of symbol, a circle, to show a roller. A roller can exert only a force perpendicular to the surface. It cannot have any force that goes side to side. So it also has only one unknown, the magnitude of the force. The third type of connection is a smooth contacting surface. A smooth contacting surface can only exert a force perpendicular to the surface. This is like a chair leg. Without friction, any force side to side will cause the chair leg to slide. So we have one unknown, which is the magnitude of the force. The fourth type of connection is a pin or hinge. In a 2D diagram, we usually use a symbol that looks like this, or a triangle. A pin can rotate, so there is no moment at the reaction, but it can exert a force in any x or y direction. So there are 2 unknowns, the fx and fy. And finally, the fifth and final type of connection we will consider in this course is the fixed support. So a fixed support cannot move, it cannot rotate, and therefore it can exert a force in any direction, in x or y, and it can exert a moment. And so therefore there are 3 possible unknowns at this type of connection: the magnitude and the direction of the force, and the moment. Moving on to 3 dimensions, there are 6 types of connections that we will consider in this course. In 3 dimensions, we can again have cables or rollers, and nothing changes about them. There's still one unknown, just the magnitude of the force. However, a new type of connection in 3 dimensions is a ball and socket joint. A ball and socket joint can rotate around in any direction, and so therefore there is no moment. But it can exert forces in any of the x, y, or z directions. And so we have 3 unknowns, which are the forces in those x, y, and z axes directions. The next type of connection that we'll consider in this course is called a journal bearing. A journal bearing allows the rod to slide along one of its axes. So it allows the rod also to rotate along one of those axes. But if we try to rotate around, in this case, the y or the z axes, it cannot rotate, and so instead a moment develops. And so this leaves us with 4 possible unknowns. there are two forces perpendicular to the direction that it can slide, and two possible moments. The next type of connection we can have is a pin or a hinge, which we saw in 2 dimensions. But in this case, we have to consider the possibility that if we try to rotate this in the direction that it cannot rotate, there are moments that can develop, which we didn't have to consider in 2 dimensions. So it can rotate in this case around the x-axis. But if we try to rotate around the y or z-axis, it cannot rotate, and so a moment develops. So in this case, we have 5 possible unknowns, the fx, fy, and fz, plus the 2 possible moments. Finally, we have the fixed support again. Since we're now considering all 3 dimensions, that leaves us with 6 possible unknowns, all 3 force directions, plus all 3 possible moments. It's important that you're able to recognize any of these types of connections and draw free body diagrams that show the possible reactions at that connection. And so I'll show you some examples of how to draw free body diagrams for rigid bodies now. In this example, we have a beam. So the first thing we want to do is we want to draw the beam by itself. Then we'll define the x and y axis. And then we want to draw the forces that are acting on this beam. We know there's one external force here. I'll call that F, and we know it's equal to 1,200 newtons. We also will know that there's weight, which is going to act in the center of gravity, which we'll talk about later in the course. I'll call that force W, and that's going to be equal to the mass, which is 100 kilograms, times the gravitational acceleration constant. And then we see that there is one connection, and it's a fixed connection. So we know that a fixed connection can have forces in either axes, so I'll call that AX and AY, and it can also have a moment, and I'll call that MA. And so this would be our free body diagram for this system. And using the information we have, we would then have to solve for AX, AY, and the moment. In this example, we have a lever. So the first thing we want to do is we want to draw the lever by itself. In this case, we're told that the connection at point A is a pin. So a pin can rotate, so there's no moment. So we only have forces, I'll call those AX and AY. We also know that there's an external force, F, and we're told that there's a spring force, so I'll call that Fs. That's equal to the spring constant times the stretch distance. And we're also told that there's a force here on B. I'll just call that B. Now the reason is because we'll find out later that this rod B is called a two-force member. And we'll talk about that next class. But what that means is that the force B will act only in the direction of the rod. So we don't have to break it up into the X and Y components. And so this would be what this free body diagram would look like. And then eventually we would solve for the reaction at AX and AY. So by now you're probably getting the hang of this process. Again, draw the member by itself. So we have this rod, and the most important thing we want to do after we put on the external forces, I'll call this F equal to 750 pounds. The most important thing we want to do is to identify what types of connections we have. So we see at point A is a pin. And again, a pin can rotate, so there's no moment, but we have both X and Y components. So I'll call this AX and I'll call this AY. But we have a roller at point B. A roller, remember, can only push in the direction perpendicular to the surface. And we know the surface is oriented at 30 degrees. So we know the force B has to act perpendicular to the surface that it's touching. And so this would be the free body diagram. Again, we have three unknowns. We have AX, AY, and the force B because we know the direction in which force B is oriented. Finally, let's look at an example in 3D. So in this case, we have this rod here. And so this will be the member that we draw in our free body diagram. And there's going to be several forces acting on this rod. So the first thing we have to recognize is that at the point O, it's a ball and socket joint. A ball and socket joint has no moment, but it is restricted in the X, Y, and Z directions. So it means we have to draw a reaction force. And sorry, this is point O, not point A. Then we'll call OX, OZ, and OY. So if we were to define our X, Y, and Z axes like this, it would mean that OY would be positive, OX would be negative because it's pointing in the negative X direction, and OZ would be positive, according to the way that we've drawn our diagram. Now it's important to remember to use the plus and minus signs in the way that you draw the diagram. So it's always important to think how you expect each force to react and draw it that way. You might find out later that, for example, OX could be equal to 0, or OX, you might get a negative answer, meaning the way you thought it reacted was the opposite of what it turned out to be. We have more forces than just the ball and socket joint. So we have the ball and socket joint, and we also have two cables attached. We have these two cables. These two cables can only have tension in them. So we know again that the force will act only in the direction that the cable is oriented. So we know the direction of the force, but we don't know the magnitude. So I'll call this tension in the chord AC, and I'll call this tension in the chord AB. And finally, we have the weight of the pot, which I'll call W. And so we would do some geometry to figure out the direction of these using the dimensions that are given to us, and then we can solve